Hi everyone. In this video, I wanted to talk about a recent article that I put up on LinkedIn. As you can see here on the screen, it's called Semantic Healing, Repairing Missing IFC Relationships Through Spatial Graphs Using Topologic Pi. And I wanted to show you the Jupyter notebook that goes along with this article. The basic premise of this article is that semantic relationships in IFC are sometimes incomplete, they're missing, and you would like to be able to discover them. And Topologic Pi can help you discover and encode these relationships that become semantic relationships based on geometric analysis, spatial analysis, graph analysis as well. So I just wanted to show you how this workflow happens. So let's get started. I have put up on GitHub under assets a new Jupyter notebook, and it is called IFC underscore healing underscore semantic underscore relationships dot IPYNB, as you can see here, and you can find it, as I said, on the Topologic Pi GitHub. So let's go ahead and run this Jupyter notebook step by step and see what it gives us. So as you know, if you've followed my work, this first cell is you don't need to run if you have pip installed Topologic Pi, because I'm using my developer machine. So first step is to import the needed classes and libraries. There are a few of them here that we need. We need a cluster, a topology, the new T-graph, the IFC class, and Plotly. Please note that this requires the very latest version of Topologic Pi. I believe it is now 0.9.59 at the time of recording this video. So we have imported those. Let's do a bit of configuration. This is basically to tell it where is the IFC file. You can use, of course, your own. I have one on GitHub as well. I'm using the IFC 2x3 duplex architecture. It's a very famous, kind of popular IFC file. It illustrates the case very well. And then it's going to output it to something called healed IFC and add a date time to it, as you can see here. And some just simple defaults for the figure, for the Plotly figure width and height, the background color, and we're going to render it in the browser. And then just to set the vertex, the graph vertex sizes and the colors and the edges, the edge width and the color of the edges in the graph. Just some defaults. All right. So the idea here with the new IFC capability is that we create an IFC model only once. So as you can see here, IFC model is equal to IFC.model by path. We give it the path. And then from here on, we use the IFC model. And here I am following the example of the excellent IFC OpenShell. Of course, in Topologic Pi now, in this kind of workflow, we are not using IFC OpenShell. I have written my own very fast parser for IFC entities, of course, with the help of AI these days. So it parsed around almost 39,000 entities in 0.335 seconds. Okay, so here I'm just getting some IFC entities and converting them into topologies so that I can visualize them. So this will take just a little bit of time. So we are building the IFC spaces. We're converting them into cells. We're building walls and slabs, etc., etc. So all of this is now conversion into topologies. So it gives you a little bit of idea what's inside this IFC file. Okay, done. So that took 21 seconds. All right, so the first step is to build a semantic-only adjacency graph. This is an adjacency graph between spaces, between IFC spaces, and it's based only on what is existing inside the IFC file. it does not discover anything new. So as you can see here, it says include semantic connections is true, and include spatial connections is false. So we're not including any spatial connections. We're not discovering anything new. We are just simply looking at the semantic connections. Now, our vertices are IFC spaces. Here you can type space, IFC space. It will figure it out. And in terms of what are the connecting element types, I'm focusing only on walls and slabs. Of course, this will also include standard wall case and standard slabs, etc., or IFC slabs. Okay, so let's go ahead and run this. It will build first of all, a semantic adjacency graph for us. And here we are just simply adding some information to the vertices so that we can figure them out when we display them. And as you can see here, that took 8.6 seconds, and it built a semantic adjacency graph with 99 vertices and 206 edges. So let's go ahead and take a look at that. Okay. So here is the graph. This is what it is existing in the IFC file. And you'll notice a few issues. For example, the very first obvious one is that this node here, which is an exterior slab, sorry about that. This is when you hover over it, it shows you all the IFC information. So it's quite a large display. But you can see that it is an isolated vertex by itself. The other issue is that if you look at this IFC slab here, which is this one here, it's made out of wood, 169354. It is connected to the bedroom, which is what IFC files do. The slab is connected to the space, to the IFC space that contains it, but it is not connected to the living room, where if it is an adjacency, you might want to express an adjacency through the slab, from the living room to the slab to the bedroom. And that is now missing. Same thing happens here. You'll notice that slabs are connected to the space above them, but not to the space below them. So you don't know, you can miss that adjacent. And this is just an example, of course, of what could be missing. This could happen in MEP files or electrical IFC files, where what's supposed to be connected is actually semantically not expressed. So the idea is, how do we connect that, and how do we control this type of additional information? So let's go back to the Jupyter Notebook and see what we can do here. So we have just visualized this. So now what we are going to do is build a spatial only adjacency graph. So we're going to say that we are not interested now in the semantic connections. You can ignore them for now and just focus on the spatial connections. So that's set to true. Now, in this case, just for illustrating the concept here, I am saying that I want to only focus on slabs. I want to heal the connections that are missing using slabs. And of course, the node types are spaces. So any space that is not connected to a slab, I would like to see if I can establish that connection. And this is where you can control the types of new edges that get added. So for example, instead of space or IFC space, you can have focus on walls or any other type of IFC entity, and just simply say, check for these types of connecting element types, and you can list them here. Now, in addition to specifying what you would like to consider as a connection, you can also decide on what constitute an edge, what can create an edge. So if the two elements, for example, touch, or if they overlap, or if one contains the other one, or if they are just simply happen to be near each other, and you can specify proximity values there in distances as well. Hopefully that also matches the units that you are using in your IFC file. So in this case, I am saying that any slab that either touches, overlaps, or contains or is contained by, it's all, it's bidirectional, or is near a space, please do an edge. Now, in terms of proximity, I'm specifying 0.2, 0.5, and 0.75 as the thresholds. So 0.2 meters, basically. So 0.2 would constitute a near, 0.5 a medium, and a 0.75 far. And you could obviously control that so that if the slab is far enough from a space, you do not draw that edge. The other thing you should control is use the shortest distance. So obviously, if you are just using centroid to centroid, the distance between the centroid of a slab and the centroid of a space might be quite large, depending on the geometry. The use shortest distance will find what are the two entities that are nearest to each other between a space and a slab. Like it could be a vertex or a centroid of an edge or part of the face, whatever is nearest. So actually, it uses the shortest distance between those two elements, and that is usually a much more reliable measure of how close something is to something else. And that's really it. By controlling these elements, by these parameters, you can create a new spatial adjacency graph. So let's go ahead and create that. Same thing here. We are just simply assigning some labels to the vertices so that we can see them. Now, this one obviously takes a little bit longer because it's doing a lot of geometrical and topological work. It does use BVH, which is a way to speed up testing of proximity and other spatial adjacency. But still, it will take for this IFC file, it will take a little bit more than a minute in order to classify all the relationships. Now, also, please realize that all the edges are imbued with the spatial relationship and the fact that they were created by a spatial adjacency graph, so that they are distinguished from the semantic relationship edges. So you can always find those out, classify them, and deal with them differently than the original semantic graph. So here we are close to getting this one complete. And then the next step would be to actually visualize both the semantic and the spatial adjacency graphs to see what has changed, what has been added. For now, up to this point in the Jupyter Notebook, those two graphs are separate. Obviously, you can union them. There are graph union operations. But you'll notice that they have 42 vertices. This new spatial adjacency graph, has 42 vertices and 243 edges. So let's compare that to what we had before. We had 206 edges. So these are completely new edges that are not semantic. These are only spatial. Now, there is obviously overlap, and the software takes care of that overlap. Obviously, it will not duplicate edges. So let's go ahead and see the result. So now I'm adding a third data structure here for the spatial adjacency graph. And I'm creating a figure from data 1, data 2, and data 3. Data 1 is the building, data 2 is the semantic graph, and data 3 is the spatial graph. Okay, here it is. The semantic graph is in blue, dark blue. The spatial graph is in orange. And you'll notice that isolated vertices are now connected. And you'll also notice that slabs like this one, the wooden floor slab, is now connected to the IFC space below it. And this is, of course, just one version of this graph. I did not say to discover, let's say, spatial relationships between walls, which could increase the density of this graph. But you can see now that you have a far more complete graph that you can analyze and do some work on. Okay, so now those are just graphs. How do we modify or heal the IFC file itself? So that will be the next step. So now we create new semantic relationships in the IFC model based on the spatial adjacency graph. So basically, it's as simple as this. You call IFC.semantic relationships by graph. You give it the existing IFC model that we created before, and we give it the spatial adjacency graph. And it knows what to do with it. It will take a look at all the new edges. It will reconcile them against the existing relationships in the IFC model. It will not duplicate new semantic relationships. Let's say if that already exists, it will not duplicate it. And if it doesn't exist, it will add it with the correct provenance that says this came from a spatial adjacency graph. It wasn't in the original IFC file, so that you can find it later on. So we run this. This goes very fast. So it created 203 new IFC relationship entities. Out of those, it matched 58 existing ones, so it did not duplicate those, and it skipped 0 edges in the graph. So all of the edges have been added correctly. And then we export this IFC model to an IFC file. And there it is. It just exported now 39,101 entities, and it saved it in this healed IFC file. So we can go there and try to find it. Let's see, where is it? It's over here. IFC. Let's go here under assets, and then IFC, and then healed IFC. You can see I've been trying a few of those. So let's go ahead and open one of those. And yeah, you will not be able really to see anything visually, anything different. But this IFC file has more IFC relationships than the original one. And you can see by the size of it, this is 2,355 kilobytes. Let's take a look at the original one, which is this one. This is 2,325 kilobytes. So it has increased in size. That is it really from me. I'm happy to answer any questions if you know of a use case that this can be useful for you. Please reach out. I'll be happy to work with you and apply Topologic Pi to a real world use case. Thank you again.